Good day everyone, this is Group 1. This is our video presentation on subtopic 7.1 Elementary Row Operations ERO. This is our group member.
I'm Yi Heng here.
I'm Kang Xian.
And I'm Khoo Yue Yang.
I'm Lim Yi Jian.
And I'm Loh Chi Yang.
And I'm Najmi.
And our session number is 35. Our course code is SSCE 1693.
Hi guys, I'm Yi Heng. So let us recall what is metric algebra before we discuss about elementary row operation. Metric is a rectangular array of numbers called elements arranged in rows and columns. A metric with m rows and n columns is called a metric of order n times n. Let us discuss about this metric A. This element A12 indicates that this element is in first row and second column. Another element A21 indicates that this element is in second rows and first column. Next, we want to talk about what is elementary row operations ERO. The operations such as multiplication or division are performed in the original metric to get the elementary metric are known as elementary row operations. There are three types of elementary row operations. Why we need to use or learn ERO? Because it is an important method to find the inverse of a metric and to solve the system of linear equations. There are three types of elementary row operations. So the first type is switching two rows. Rows can be moved around by sweeping any two rows in a metric. It is denoted by this ERO symbol. Example, interchange row 1 by row 2 in a metric A, and this will be the result. Next, the second type is row multiplication. Multiply each element in any one of the row by a same non-zero scalar. The ER symbol is alpha times any rows, where alpha is a non-zero scalar. Example, we consider this a method matrix. We perform this row operation, which is second row multiplied by 3. So each element in second row will multiply by 3. So you can see this 5 multiplied by 3, 0 multiplied by 3, and negative 2 multiplied by 3. So this will be the result. The last type of ERO is row addition. I row is added by j row that is multiplied by the scalar alpha. This process can be denoted as I row plus alpha times j row, where I is not equal to j and alpha is not equal to 0. The purpose of this process is to change the element in the I row. For example, consider this matrix. We perform this row operation, second row plus 2 times first row to this matrix. This row operation also means that second row equals to second row plus 2 multiplied by first row. As you can see here, 5 plus 2 multiplied by the element in first row, same as here, and this will be the result.
Hello everyone, I am Kang Xian. Now let us move on to the simple question to get an idea of ERO. Question 1. Perform the row operation R1 interchange R2 on the following matrix. In this question, we want to change the row 1 to the row 2 and the row 2 to the row 1. So the answer will be the row 1, 2, 4, 5, and the row 2 will become 4, 8, 3. Row 3 will unchanged, so we just write 7, 1, 2 in the row 3. Okay, next question 2. Perform the row operation 3 R2 to R2 on the following matrix. In this question, we want to multiply 3 in the row 2, so the answer of the row 2 will become 6, 9, 0, and the row 1 and the row 3 will unchanged. For the question 3, perform the row operation R1 plus R2 to R2 on the following matrix. In this question, we want to plus the row 1 and the row 2 in row 2. The row 1 will remain unchanged. The change is only for row 2. So the row 2 answer is 2, 11, 5. And the row 1 we just write 2, 3, 4. Last question. Question 4. Perform the row operation R1 plus 2R3 to R1 on the following matrix. This question combines question 2 and the question 3. So, in the R1, we want to plus the 2R3 in the R1. So, the answer in the R1 will become 11, 23, negative 9. And the row 2 and the row 3 will unchanged.
Hi everyone, my name is Khoo Yue Yang and I am from Group 1. I would like to discuss with you what is echelon form. Echelon form means that the matrix is in one of two states: row echelon matrices REM and row reduced echelon matrices RREM. This means that the matrix meets the following three requirements. The first one is the number in the row that is called a leading coefficient is always 1. Please note that some authors don't require that the leading coefficient is 1. It could be any number. You may want to check with your instructor to see which version of this rule they are adhering to. Second, every leading one is to the right of the one above it. Third, any non-zero rows are always above rows with all zeros. This is the example of echelon form. The following examples are of matrices in echelon forms. And these are the following examples that are not in echelon form. Let us see matrices A. Matrices A is not an echelon form is because it does not have all zero rows below non-zero rows. Here. And let us see matrix B. Matrix B has a 1 in the second position on the third row. Here. For row echelon form, it needs to be to the right of the leading coefficient above it. So in another word, it should be in the fourth position in place of 3. And let us see matrix C. Matrix C has a 2 as a leading coefficient instead of 1. And matrix D is not in echelon form is because matrix D has a negative 1 as a leading coefficient instead of 1. So, another way to think of a matrix in echelon form is that the matrix has undergone Gaussian elimination, which is a series of row operations. And also please note that the echelon form of a matrix isn't unique, which means that there are infinite answers possible when you perform row reduction. Row reduced echelon form is at the other end of the spectrum. It is unique, which means row reduction on a matrix will produce the same answer no matter how you perform the same row operations. What is row echelon matrices REM? Row echelon matrices is a matrix in row echelon form if it meets the following requirements. The first one is the first non-zero number from the left, that is the leading coefficient, is always to the right of the first non-zero number in the row above. And the second is rows consisting of all zeros are at the bottom of the matrix, like the example below. This is matrices in row echelon form. The A can be represented by any number. Technically, the leading coefficient can be any number. However, the majority of linear algebra textbooks do state that the leading coefficient must be the number 1. It is better for us to use 1 as the leading coefficient in each row. If the leading coefficient in each row is the only non-zero number in that column, the matrix is said to be row-reduced echelon matrices, like the example below. This is a 3 times 5 matrix in reduced row echelon form. Furthermore, what is the row-reduced echelon matrices means? So the reduced row echelon form is a type of matrix used to solve systems of linear equations. Reduced row echelon form has 4 requirements. The first one is the first non-zero number in the first row, that is the leading entry, is or must be the number 1. And the second is, the second row also starts with the number 1, which is further to the right than the leading entry in the first row. For every subsequent row, the number 1 must be further to the right. The leading entry in each row must be the only non-zero number in its column. And the last one is, any non-zero rows are placed at the bottom of the matrix, like the example below. This is a 3 times 5 matrix in reduced row echelon form. And also please note that A and B can be any value. That's all from me. Thank you.
Okay, so now I will discuss some examples on how to determine whether the matrix is a REM or RREM. For the first matrix, we can see that there is all 0 rows at the second row, so it doesn't meet the criteria of REM. This is because all 0 rows must be placed at the bottom of the matrix, so it is a neither. Now for question 2. We can see the leading one at the lower row is further to the right compared with the leading one in the upper row. So it is a REM. Now we determine isn't it a RREM. So we can see the element in the column of lower leading one has a non-zero value, which is 2. Therefore, it doesn't entitle in the RREM. So for this matrix, it is only a REM. Now moving to question 3. We can see that the lower leading one is farther than the upper leading one. So it is a REM for true, but not a RREM, because we can see the column of the lower leading one has a non-zero value 40. So it is the same as the previous questions, which is only a REM. Now for question 4. We can see 2 is the leading for the upper row, so it is not a REM. This is because the property states that for REM, the leftmost non-zero entries must be 1, so it is a neither. Now for question 5. We can see the lower leading one is also farther than the upper leading one, and the all 0 row is at the bottom of the matrix, so it is a REM. Then we see the both leading one columns has zeros everywhere, so it is also a RREM. So this matrix entitled in both REM and RREM. Now we're going to question number 6. We can see that the positions of leading one is going further and further down the row, and the column of all leading one has zeros everywhere, so it is a REM and also a RREM, and it is same as the previous questions. Now we move to the next slide. Now for question 7, we can see the second row leading one come before the leading one at the upper row, so it is not a REM. Thus, it is a neither. Now for question 8, we can see that all the elements in the matrix are 0, and the criteria of REM is that the particular matrix must contain at least a non-zero row, so it is not a REM. Now for our last questions, we can directly know it is not a RREM. It is not a REM because we can see that all the leading ones are in the same positions, which means it doesn't meet the criteria that the lower row leading one must occur farther to the right compared with the upper leading one. So that it is all of my part. I will pass to the next person. Thank you.
Hello guys, I'm Loh Chi Yang. I'm going to explain about the rank of a matrix. The rank of a matrix is the number of row that has at least one non-zero elements in the REM or RREM. So the non-zero elements is like, look at the first matrix in the left column down part there. You can see the first row, it got a 1 there. Second row, it got a 1 there. Third row, it got a 1 there. And these one are the non-zero elements. Then let's take a look on the second matrix there. The row 1, it got 1, 2, 3, 4. Yeah, all 4 of them are the non-zero elements. Let's see the last row of this second matrix. It is 0, 0, 0, 0. These zeros are the 0 elements. And let's back to the definition first. The rank of a matrix, for example, rank of matrix A can be put as PA. Okay, now let's look at the example. We count the number of rows that has non-zero elements in this REM. So let's see the first example there. first row have the non-zero element, second row also have, third row also have. So the rank of this matrix is 3. And then let's see the second example. First row have, second row have, third row have, and then fourth row is no any non-zero elements, so the rank is 3. Next, I'm going to explain steps to reduce a matrix to its REM form and RREM form. Okay, let's look at the example of REM and RREM. Here are some diagrams. Okay, the example of REM is like the diagram step 5. The X there means that it can be any other number, that would be REM. And the example of REM is like the diagram step 6. And also, I have shown the diagram of the matrix you should get in each step from step 1 until step 6. Now, let's start with the first step. Firstly, we have to make the leftmost non-zero element at the first row at the first column to become 1. So we can use 3 types of ERO. The first type, interchanging the rows. Second type, multiplying the rows by a non-zero scalar. Or third type ERO, row addition. Here's a reminder, the interchanging the row only can be used in step 1. Second reminder, we have to avoid to get any fraction in these early steps. Let's see the example now. Step 1, we can do the first type of ERO, interchanging the rows, follow the direction of arrow. So let's see, we're going to do the interchanging the row for example matrix to become matrix alpha. We do R1 interchange with R2 for example matrix, so you will get matrix alpha. Or you can use second type of ERO, row addition for example matrix to become matrix A. We do R1 plus negative R2. We will get 2 minus 1, we get 1. 3 minus 3, we get 0. 4 minus 3, we get 1. You will get matrix A. Then, in step 2, we're going to use the leading one in the row 1 to change the elements in the column 1 that below the leading one to become 0 by row addition. Okay, let's see the example. So in step 2, we want to get the matrix like the diagram step 2. We want to make the elements below the leading one to become 0. I'm going to do the row addition R2 minus R1 and R3 minus 2R1 to matrix A to get matrix B. Next, step 3, we apply the first step to the leftmost non-zero entry for the second row to get the leading one. So let's see step 3, we will get the leading one in the second row. So let's continue with matrix B. We do row addition also, R2 minus 2R3 to get the leading one in the second row. Then once again, you will have to get the zeros in the leading one column. Step 4 here, change the elements in the column 2 that below and above the leading one to become 0. We will do row addition to get the diagram of step 4. Then, step 5, we repeat the above steps until we obtain the REM. We will do the ERO again to get diagram step 5. The pattern is like this. In step 1, we will get the leading one in the first row. Then, we make the elements in the column to become 0. And then step 3, we get another leading one in second row. After getting the leading one, we make the other elements in the column of leading one to become 0 also. Then step 5, we repeat it to get the leading one and then to get the columns of it to become zeros. Until step 5, you will get the REM. And until step 6, you apply the second step for the element above and below the leading one to become 0. So you will get like diagram step 6, the REM. So these are the reducing steps for the REM and REM.
Hi guys, I'm Najmi. So I'm going to show you how to solve a question in this topic. Okay, so the question gives us matrix A and want us to find REM, RREM and rank of matrix. Okay, for the first question, we need to find REM for matrix A. Since the first row already have 1, we need change second and third row into 0. So the operation that we need is R2 minus 2R1, R3 minus 3R1. Then the answer that we got, the first row remain the same, and for the second row we got 0, negative 7, negative 4, and for the third row we got 0, negative 5, negative 10. Okay, for the second step we need to change this to 1. So the operation that we need is negative 1 over 7 multiplied by R2. Okay, so the answer that we got is first row remain the same, second row we got 0, 1, 4 over 7, and third row remain the same. And then for the third step, we need to make this become 0. So the equation that we need is R1 minus 2R2 R3 plus 5
R2. Then the answer that we got is 1, 0, 13 over 7, 0, 1, 4 over 7, 0, 0, negative 15 over 7. And then for the final step, we need to multiply third row with negative 7 over 50. Then the answer that we got, first row remain the same, second row also remain the same, and the third row we got 0, 0, 1. Okay, so that's the answer for question A.
Since we already got REM from question A, so we just need to continue to change it to RREM. So the first thing we need to do is change this to 0.
So to change this to 0, we need to R2 minus 4 over 7 R3 and R1 minus 13 over 7 R3. Then the answer we got 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, so is the answer for question B, RREM. So lastly, for question C, we need to find rank of matrix A. So the rank of matrix A should be 1, 2, and 3. There is 3 rows of non-zero, so the rank of matrix A is 3.
So at the end of the video, we have learned the definitions of metric algebra, definitions and type of elementary row operations, which is the ERO and echelon form, and also how to determine the rank of matrix and the reducing step of matrix to its REM and RREM form. Last but not least, some problem solutions. So that's all of our videos. Thank you.